It is my distinct pleasure to welcome Alex Bayen to our Georgia Tech community to talk about his project Mobile Millennium. Alex is a graduate of the École Polytechnique, which I probably just butchered, in France, and then went on to do degrees in aeronautics and Stanford, and is now a professor at UC Berkeley and has been there since 2005. His earlier project, Mobile Century, led to the current work with Mobile Millennium, and I think many of us are very excited to hear more about this project because of the linkages with our existing work. So with that, I'd love to turn it over.
Thank you very much. Well, thank you, Karen, for the introduction. I'm very happy to be here today, and it's also fun to see a lot of friendly faces. So today I'm going to talk about the use of smartphones in transportation in the very specific context of traffic information and traffic management. And so the general area, I guess, of the work I do is large-scale infrastructure, instrumentation, and operations. And these can span many subfields of civil engineering, such as structures and environmental monitoring, smart grid, and transportation is really going to be most of the focus for today. I mean, if we think about transportation as this kind of classical system that was built over decades and even centuries, I think part of the infrastructure that monitors it has provided great breakthroughs in the past decades, in particular for monitoring the backbone highway system in many states of the US, but that infrastructure has inherent limitations, in particular with scale and deployment. And I think one of the very interesting things about transportation in the last 4 or 5 years is that it's one of the first indirect beneficiaries of the explosion of smartphones that we've witnessed in the last couple of years. So this curve is quite fascinating. It's the number of devices sold as a function of time in log scale. The PC is quite phenomenal. What you probably see is the Android and phone curve on the far right here. Today there's 1.3 million phones, operating device like Android, which are turned on every day. So 1.3 million Android phones turned on every day, and that gives you a scale of billions of phones on the planet, and there's already more than 1 billion smartphones on the planet. And so transportation has greatly benefited from it. So the story I want to tell today is how in a couple of years we went from this system to this system, and I think all of you who have run Google Maps and Google Traffic and similar traffic feeds on your phones or on the web are now used to this, which not only shows freeways, like you had 4 years, 5 years ago, but also shows arterials. And the difference is that, we've reached a point where critical mass has enabled to provide traffic information at that scale. And that's the first part of what I want to talk about, is how we went from this almost antique system, which had been very resilient and robust for many decades, to something which is moving really fast and will enable next generation traffic management. So the goal of the talk is really twofold here. I think the first part is going to be slightly frustrating because I won't have the time to go in depth into some of the work we had to do for this Mobile Millennium project, but I will take the time in the second part to do a little bit of a deep dive into some of the algorithms we're building for our current project, which is really an outgrowth. So I think for the first 10-15 minutes, I'll have to stay a bit superficial because there was too much to present, but hopefully we'll have a chance to dive together. So Mobile Millennium was the first traffic app ever deployed on RIM and civilian phones in North America to gather traffic information from GPS-enabled smartphones. At the time it was phenomenal. We had more than 5,000 downloads, and remember this was pre-iPhone, pre-App Store, pre-Google Play. The numbers were very different. Of course today, a university like ours is not in the business of maintaining and deploying and operating a traffic app. In fact, what we do instead is have brokering agreements with a lot of the different companies that gather that data for us, as opposed to the initial phase. And today we're gathering 60 million data points every day, so GPS data points that we use to construct these real-time maps like you see on Google and Bing and all these other systems. This is a kind of a nice nostalgia, dive into nostalgia. It was the super high-tech phone we used at the time when we launched it, and of course today it looks completely antique, but we still like to display it because that's a historical landmark for us. And we've deployed this in other cities, in Sweden, for example, and Stockholm with the 7 routes of Stockholm. And this is something that we're currently and ongoingly use for research and development. And so that's what we're building our work on. Now, it started as an experiment called Mobile Century, and that's mainly because the California Department of Transportation wanted to see it work. And what that meant is more than writing a research paper, really show it with real people and real phones. So in 2008, we basically hired 200 students, asked 165 of them to drive back and forth 10 miles for 10 hours. That's a bit of a boring job, but we paid them well. And then we asked 40 others to basically monitor and help us do the logistics on how you do this. And the goal at the time was to achieve 2% of penetration of traffic. So that number was actually very carefully chosen. The goal was to, 2% was the forecast penetration of phones 18 months after the experiment. That's what the market's growth trends were showing. So the goal was to see, okay, in 18 months, when we would have that penetration, what could we do with it? So we ran that experiment in 2008 with a full command center and teams monitoring the whole thing. We even had teams of students on bridges with high-resolution video cameras that could record all the license plates of all vehicles, not only our vehicles, as they were crossing through the bridges, which would provide an alternate source of data to validate the thing. So it was a quite involved logistics operation. And while we were doing it, we were basically holding a press conference with Bob Anucci, who was the CEO at Nokia at the time, which was the main industry partner, and Randy Iwasaki, the director of Caltrans. If you had been in a helicopter, this is kind of, well, these guys are lost, so that's an exit, but this is what you would have seen. The color indicates the speed of each of the vehicles, and this happened when we had a live display of traffic, and this is probably the first time in history that there was ever a constant broadcast of traffic for 10 continuous hours of traffic information that was exclusively gathered from smartphones. This was very stressful because the press was there, the media was there, and there was an accident. It was not our vehicles, and we happened to record the congestion faster than it happened on all the other websites, including the California Highway Patrol, which was great because people initially didn't believe us. In fact, that person worked at traffic.com, and what she's doing on that picture is calling our friend to figure out whether the Berkeley algorithm was completely broken, and because there should never have been congestion here. And it turns out we caught it faster than the others. And the rumor goes that we created the accident to demonstrate the technology. That certainly came from Stanford. This is the architecture of what we built. Now we rebuilt it 3 times because the first we built it in MATLAB, the second we built it in a professional system, and then we had to rebuild it another 2 times. But that's what it takes to build Google Maps. I mean, Google Maps has a lot more, but if you want to build a traffic feed on some map, basically you have a bunch of feeds. And the point is not to go in all the boxes, but to see the architecture. And then they go into filters that feed models, on which you feed estimation, so data assimilation, that provide information that you feed back to the customers. And so this system is several million lines of Java code. It's been live since 2009, and that's what we're operating today, and that's what we're using to test all the research and algorithms we implement. So to give you a sense of the scale of the data, that's what 0.5% of our data looks like. This is a particular case of data we can show to the public. Most of the data we cannot even show, we cannot even redistribute for confidentiality reasons and commercial trade secrets and all these arguments that companies give you to not show their competitors what they have. But that we can show because that's the taxi fleet of San Francisco. These are 500 taxis that send us their feed every day at the 1-minute rate. So 1 point is like this inverse Pac-Man display. 1 point is basically 1 GPS point every minute, and the red dot is basically the vehicle moving. Right now it's early morning, so there's not much traffic, but as the day grows, there's more traffic, and at the end of the day, you can basically draw the whole map, and you can infer the topology of the network quite accurately, and it's pretty cool to see that the taxis go really far. So the point is, I think that 0.5% of data gives you a sense of the scale of the data we deal with, and that's what powers our engine, and I think that's what was not even thinkable in 2007 when we started the project, and that's something which has been almost entirely commoditized by the private sector in the last couple of years. So I'm going to go through 3 challenges that you encounter when you build these systems at a superficial level, and then I'm going to dive deep into one of them, which is what we're doing now. The first challenge is obviously privacy, and when we started that project, in fact, this is the first movie we ever recorded with a phone gathering a GPS track. For those of you who know Juan Carlos Herrera, already does, that's where he lived at the time, and we use this as an example of how you can use phones to breach privacy. You can see all traffic speed violations and traffic light violations, as well as a lot of interesting things there. And so the point there was to show that it's not a good idea to just gather tracks, even if you anonymize them. People at Microsoft have shown back in 2006 and 2007 that you can re-identify by correlating with other feeds, so bad idea. So the first thing we have to do is to build an architecture that supports privacy by design sampling. And the way it works is when you're running a client, basically the phone downloads the map, and it could also download a lot of hidden objects in the map, such as VTLs, which are virtual trip lines, which are geographic markers that are defined by GPS coordinates and can trigger a phone update probabilistically in a way to avoid privacy intrusions. And so the way it works is, instead of sending your data all the time, what you do is upon crossing one of these markers, you probabilistically send information such as, hey, I'm a phone, that's where I am, and that's how fast I'm going, but you don't send all the other stuff. And if you do this, and if there's enough vehicles doing this probabilistically and you don't systematically transmit, then you can show that a lot of the issues of privacy can be solved quite easily. And so, in terms of the mathematical contributions you have to make this work, I mean, there's all the architectural work, and in fact, that was patented as early as the end of 2007 by Nokia, following the work we did together. But then there's a lot of other algorithms based on Hamilton-Jacobi equations that you can use to try to re-identify travel time, even if you don't have the identity of the vehicles that go through these markers. And so, a lot of the work early on in the project was really to define mathematically what these solutions mean, how you compute them, and so on, and potentially then do all the data assimilation from techniques which are, in fact, I think Ted just walked in, but which are very similar to what's done in environmental engineering, where you use sequential data assimilation to put that data into models. And so I'm going to move on to the second challenge because, again, I can't go in depth with all these topics, but this was certainly one of the first challenges we had to deal with. The second challenge is the data is just crappy. And when you deal with crowdsourced data, that's just the way it is. You have tons of data, a lot of it is very low quality, and you have to make the best you can out of it. And you can't just do the naive thing. And the naive thing here would be, in San Francisco, a cab can go up to 7 blocks in 1 minute. Here it's pretty congested, so it actually goes pretty slowly. But if you just do the naive thing, which is to project it on the map, because by the way, no GPS points ever falls on the map, so you have to project it on the map. But if you look at 9 and 10, 10 is actually behind 9, and that's because the guy is stuck at the traffic light. So GPS error, 1 minute later, actually puts him behind where he was when the guy actually did not move. So typical algorithm would have the guy go around the block, because that's the most logical thing with these positions. So the point is, when you just map match, it simply doesn't work. And so a lot of the work we had to do early on to actually make good use of that data and avoid these completely crazy things that you would come up with, like here it projects on that road, but the cab clearly goes this way, and we know this because we had a validation data in it. So this is completely wrong. And so a lot of the filtering algorithms that we developed have to work in sequential phases where you don't project on the road network, you project on every possible point within an error bound of where you think you are, and then you compute all the possible paths from these different position sets. And then by using machine learning technique and understanding how vehicles actually drive, and taxis drive a very different way than people do, for example, who drive a taxi, then you can build a model from which you can extract travel time distributions and potentially make information. So here the point is to show that GPS data is phenomenal, it's massive, but it's actually quite difficult to use. And so the contributions we had to make there were more on the line of combined path discovery, map matching, and then figuring out when data self-contradicts, and that can be identified quite easily with Hamilton-Jacobi equations, and then use stochastic queuing theory to reconstruct travel time from these, because you can't even figure out how fast people are going, it just doesn't work in the arterial network, so you have to use a degraded version of traffic information, which in that case happens to be travel time. And maybe the last challenge I want to talk about is data assimilation. Data assimilation is a field which is common to many subfields of civil engineering, and certainly in traffic, it's been quite interesting. And you can think about data assimilation as follows. I mean, in the context of traffic, your vehicle's transmitting some Lagrangian data, so it's mobile data. And if you're trying to map the evolution of speed as a function of time, you're basically getting a surface. So the job of figuring out what speed on the freeway is now is the reconstruction of that surface from this mobile measurement up to now, that's Nowcast. And the process of predicting what the speed will be in the future is forecast. And if you can do this, then you can start to do anticipation and management. So first, we started doing Nowcast, and for this, we had to use a model which is fairly known from the applied math community and the transportation engineering community. It goes back to the 50s. That's called the Lighton-White-and-Richard equation. It's a first-order hyperbolic PDEs, scalar with a concave flux function. In order to avoid mathematical jail, you have to pose the boundary conditions using the weak boundary conditions in BV space. And if you do that, then you're going to be fine. The flux function is also fairly known in the transportation engineering community. It models the flux as a function of density. The more people, the more flux, until traffic jams happen. And then traffic decreases, and when the density is too high, you're stuck on the freeway, the flux goes to zero. It's a fairly seminal model, mathematically very nasty because of the functional space you have to work in, but fairly robust and certainly fairly accepted in the community, which in order to compute numerically, you need to discretize, and there's been a fairly well-known scheme since 1957 called the good enough scheme, which appeared in the transportation engineering literature in 95. And so basically what it does is it takes that density function rho and it discretizes it. So I is the cell on the freeway, and is the time step, and this is just an update equation for the density. So if you're a control theorist, you can view this as a gigantic nonlinear dynamical system, which has all the nasty features you would think of, which is non-smooth, non-linear, and non-differentiable. So that's really bad. And that's what you are using as a backbone for your estimation algorithm. One thing to keep in mind here is that there's a flux function here, which I don't have time to write, but it's pretty nasty. Now the thing is, with a smartphone, you don't measure density. Okay, you can measure how fast you're going, but you cannot measure how many cars are around you. So you can't just use this as is. And the main question you have to solve is how to map this into an equation for velocity. Because it's going to be some time before everybody has a smartphone using the same apps transmitting to the same data provider. So until that's the case, you have to use another equation. And part of our contributions was to create that equation for velocity, which means now you're not looking at speed, but you're looking at evolution for velocity. That came at the cost of some mathematical work. And skipping the details, what you end up with, the point is not to look at all the equations here. The point is to look at the second equation, which says, you know, my velocity now is what it was before, integrated in some function, which can be also computed with these good enough fluxes. If you've done numerical analysis, it's really one of the first things you learn for hyperbolic PDEs. If not, just you take this as an update equation. And again, the nasty feature here is nonlinear, non-smooth, non-differentiable. So you have to live with it. But that's what you use to do estimation. And so our early contribution was to use that with a measurement equation. And here the beauty is that with a phone you can measure how fast you're going. So you can read the velocity in some places of the network, and you can reconstruct it using these estimation techniques we've worked on. And the beauty is that the observer equation is linear. And what that means is that the measurement is basically a reading you get from the phone directly, so that H matrix is a matrix full of 0 and 1s. It just reproduces what you can measure, and you add some noise to it. And if you've done estimation, that's just saying the linear observer, there's a linear observer there. And so the standard techniques that are used in meteorology and control and many other fields are a use of that mathematical framework. And it's basically a cycling between measurement update, okay, and model forecast. So at every step, you model your system forward in time, and then you correct it by what you see. And because the system is non-differentiable, you can use techniques like Kalman filtering. You have to use statistical methods like ensemble Kalman filtering, which are fairly commonly used in meteorology. And that's what we had to do initially. So again, here, it's probably the end of the first reading part of the talk, and then I don't have time to go in depth here. But what I want to do is to show some of the ideas we had to put together to create that system. And these work quite well. These are the Kalman equations, and I'm just going to skip them, but I'm going to show how they work on the data. So this is paradise. This is if you have 2% of traffic, that's what it looks like. You have one GPS point every 2 minutes, every 2 or 3 seconds, and you can basically read traffic. So there you probably wouldn't even need much algorithmic work, because you could see people going like this is time and this is space, people going really fast into congestion, and then slow and then fast again. But that's paradise. I mean, life is never as nice. So the truth is, what if you only had a subset of that data, like VTL data I showed before? Or what if you just had a sampled version of this? Then it's not clear what traffic looks like. And so what the ensemble Kalman filtering algorithm I showed before do is basically reconstruct that, okay, from the data. And so initially in our work, we did a lot of downsampling work. We had a lot of penetration, figure out what would happen in the real world, like nowadays, and then be able to reconstruct and assess how good the reconstruction is. And so that was essential in building that system and making that system work. And this algorithm has been launched in all of Northern California at the beginning of 2009, and has been live since for all of Northern California. And so initially people really asked me, well, how is that different from Google? And well, I mean, in a sense, at that time, in 2008 and 2009, everybody was more or less chasing the same rabbit. It was like everybody was trying to put traffic online. And so we did a lot of comparison with what Google provided at the time. And so I'm going to show you one movie where you can see the Google feed and our feed at the same time. And I think what was interesting there is that at that time we were reporting traffic jams about 15 minutes earlier to Google. So on the left you have the Google feed, on the right you have our feed. And it turns out there's an accident here, like almost every day there's an accident here. Going into the bridge, hiding the accident where the action happens. And so typically, the way you see the accident is it happens right there at the merge, and then you'll have a queue building up that's predicted by the hyperbolic model, and you'll see this turning all red very quickly. And so, the time is accelerated here. It's like a frame is 30 seconds. But the point here was to show that these methods work quite well. They're really fast. And at that time, they were certainly much faster than the state-of-the-art in the private sector. And Google ultimately shows it, and well, it's interesting, it's all yellow. And if you have 3 colors, you can't really go wrong. But we were using the whole color scheme at the time. And when this movie was initially recorded on Friday the 13th of March, so the students really tried that day because they thought that it would be the best day to bet on accidents. But unfortunately, the recording device for the movie didn't work, so we had to wait for the next accident the next Friday to record the movie on a not as severe accident. You're going to think we love accidents, but we really don't. Here, I think the contributions we had to make were of several different types. We had to work on models because there was no model for speed. I mean, until 2007, there was no global way to measure speed other than having your own equipment. And if you measured speed, you might as well measure counts. Now we have a lot of speed measurements. We don't have many counts, but you need a model for it. We also needed new data assimilation schemes for it because these models are specific, and to make them run faster, you needed to have the proper algorithmic treatment. And that generated a lot of fun work on Hamilton-Jacobi equations, which was really things we did back in 2010 and 2011. And so that kind of concludes the frustrating part of my talk, where I can just tell you about high-level results. The next thing I'd like to do is to dive a little bit deeper into what we do now. I guess before I do this, the one thing I want to say, which I think was very satisfying for both the students and the staff overall, the whole project, is that, if you look at all the major players in the field, we have interacted with almost all of them in any capacity over the last 4 and 5 years, and that's very satisfying because this field is very mature. It's mostly migrated to the private sector, but either way you look at it, this was created in partnership with Nokia, Nowcasting, and Telenav. They actually funded this work, and so it was implemented in their system directly. And even though we couldn't work with Google directly at the time because Nokia had 40% of the market share, and these were really competitive times where the two companies couldn't be working together, now we do, because the situation of Nokia has changed, and so now a lot of my students, in fact some of them work at Google Zurich, where the traffic operation is run, and these algorithms are in the process of being implemented and tested on Google data. And the other companies, like the ones you can never work with, like Apple, because of secrecy, have hired our students or former staff people to basically build that for the iPhone, the latest release of the iPhone. I don't know this because nobody knows what my students are doing at Apple, but I think that's what they were hired for, and certainly, and they can't tell me, and of course, and same deal with Microsoft. And so I think the reason why I'm showing this is that I think this is a very nice example of how something which was started in 2007, which was not even thinkable, is now a complete commodity and run across the private sector. Now, where are we going with this now? So now, you can pretty much see anywhere in the world. I think Google traffic is deployed in 72 countries already. You can pretty much see traffic everywhere in the primary and the secondary transportation network, so not in the rural roads, not in the, I would say, residential streets. And that means you can probably access a lot of people there, and you can try to figure out how to use this to route people better through the network, and that goes into what we're doing right now. So the next thing I want to do maybe in the next 10, 15 minutes is to take one algorithm for routing we've been working on for the last couple of months, and explain how we would use this in the context of social networks and how you could incentivize people to do something which is better for society as a whole, i.e. try to equilibrate traffic among different road network links. So the idea is you want to use that information to redistribute traffic in a more optimal way. And the setting we've chosen, unlike in the previous part where we really put it to practice, we had to deal with the dirtiest model and data there is, this is still idealistic, and there's still a lot of theoretical work before we can reach the same level of maturity. You will see it in the models, but the point is you have to understand the simple case before you do the real thing. And that was the same with the first phase historically as well. So here the situation we're looking at is simpler. We have two cities, say San Francisco and San Jose, and you have thousands of people commuting from one to another every day. And typically you only have 4 routes really. You have 280, 101, and if you're crazy you could cross the bridge and go 880, and if you're really crazy you could go 680, but the point is there's only 4 ways to go from one to another. So in terms of network analysis, it's a parallel network, and you're trying to route a certain amount of flows and allocate that amount of flow between the different links, and try to minimize the overall cost function, which encompasses the total travel time of everybody involved. Okay, so you have a latency function, which is the time to travel on the link. You have a flow, and the total time spent on the road on that link is the amount of flow time, the time it takes to travel the link. It's a static problem formulation, there's no dynamics there. And you try to minimize this for all of the network. Now, the game is, if you give people information, they'll route themselves differently. If you give them rewards, they'll route themselves differently too. You could incentivize people to take a different route for a coupon, for a free cappuccino at the local Starbucks if you have a partnership, or for any kind of reward. And if you have the right incentivization model, they do this in Singapore, they do it in lots of different places, and you can do it through apps, through information distribution and many other things, then you can start to route people as you wish. And that's where the field is going, and that's what we're interested to do. And then you can compute what's called the price of anarchy, which is the cost of a Nash equilibrium, which is the cost of what happens is if everybody behaves selfishly, over the cost of the social optimum, which is what would happen if people followed what they were told, and that means some people would take a longer route so that society as a whole benefits. That's called the price of anarchy. And so what we're going to try to do now is to see first how to quantify this, and then how to create a Stackelberg game on it, which means now if you could control a fraction of the population, how should it be controlled in a way that society benefits as a whole? So the notion of a Stackelberg game here is relatively intuitive. It fragments the population in 2 categories. The first category are the people who are going to be selfish and are going to try to do what's best for them no matter what it does to society. And the second fraction of the population is going to be what we call compliant people. And these would be people who would be ready to take a reward, to take a little penalty on their commute. So I'm ready to take $5 or a lottery ticket or a free cappuccino to waste an extra 10 minutes of my travel time, or to take a route which is 10 minutes longer. So you have a total flow amount of R that you're trying to push through the network, and you have a proportion alpha, say 2%, 3% of people that you're going to route differently. They're going to do something good for society. And you have the proportion 1 minus alpha, the rest of the people, who are going to do the selfish thing. So you call S that fraction of compliant people, and you call T of S the reaction of the non-compliant people, the people who are going to readjust themselves selfishly based on what the good guys do. The good guys or bad guys, different terminology. And what you're trying to do as a planner is to optimize the overall travel time of the compliant and the non-compliant people altogether, given that you can only control the compliant people. Sorry, this is annoying. I don't know what's happening. Computer doesn't like the word, that's it. If you can compute the best such equilibrium, well, that's what's called the optimal Stackelberg equilibrium, and that's the best thing you could do as a society if you could only control a certain fraction alpha, 2%, 3% of the people. And the interesting thing is that in internet routing literature, that problem is actually NP-hard. And that's because the latency function on the internet has a very specific form. The latency function in transportation is actually much more complicated, but ironically, that makes the problem polynomial time solvable, which means, in our case, it's really good because it can be solved very quickly. So going back to my latency, we saw this in a couple of slides ago. The flux of traffic on the freeway increases linearly, or some ways, as density goes up. And at some point, it starts to go down, and if you get there, you're really packed on the freeway and you're not moving, technically, your travel time can become infinite. what that means is that if you look at this triangular shaped diagram, and it also works with untriangular, but that's a bit more complicated, you have free flow, you have congested, and if you look at the way your latency changes, the more density, the way the latency works, initially it's flat, right? Because whether there's a few people or a bit more people on the freeway, people all go to the same speed, roughly the speed limit, so the latency is flat. But at some point, when traffic starts to increase, then latency goes up very quickly, and if you're stuck on the freeway, technically your latency goes to infinity. So that's the latency function we have. It's very different from the internet routing literature, because in the internet routing literature, the shape is quite different. The interesting thing is that this is actually not a very useful way to plot it. What you really want to plot it is as a function of flow. As a network control person, I like to push flow in the freeway. So I'm looking at that latency function as a function of flow. So it's the same graph as before in a different coordinate system. So if you push more flow initially, it doesn't change the latency. It's uncongested, m equals 0. But if you push more flow, at some point you reach a congestion point, and if you try to push more people, actually you decrease the flow in the freeway. And that's like more and more people want to go on the freeway, but the flow actually decreases, so your latency goes up, and that's a multi-valued function. And we're going to use it this way because that's the way you can characterize Nash equilibria in it. So maybe now is the time to stop me if that function is unclear, because if this is unclear, everything else is going to be incomprehensible. But that's the main tool we're going to use here. And that latency function is very closely related to that fundamental diagram. It's just characterizing the fact that if there are too many people on the freeway, then latency goes up really quickly because you're not moving. Okay? So,
I have a question.
Yeah.
Does your approach rely on the triangular assumption of the, or does it just need to be concave?
Right. So in terms of the PD to be post, all you need is concavity. But if you have a nonlinear portion of the fundamental diagram in the free flow, that part won't be flat. And the notion of Nash equilibrium, which will be much harder to define, for a reason which will appear very clearly in 3 slides. Now, that part could be anything you want, as long as it's concave. But it's very useful to have a linear part here. So, I think the general concave part is still something we need to figure out in that context. So you need to make some assumptions, like the one I just mentioned. And now let's think about what a Nash equilibrium means for that system. So in a Nash equilibrium, everybody behaves selfishly. There is no incentive to switch path, because that's the way it's defined. And what that means is that if you have several roads chosen by the people, so first road is really fast, first road is really fast, second road is a bit slower, third road is even a bit longer, in a Nash equilibrium, everybody's equal. That means the latency, whatever it is, say 30 minutes of travel time, if you're on that road, you're going really fast because you're a free flow. That's because the road is very long. But you're going fast all the time. So this is someone like me who would want to go on 280 really fast and never be stuck in traffic. At the end, you still have the same travel time as if you're on this road, where you're really packed. You go for a shorter distance, but you're really packed all the way. So Nash equilibrium looks like this. Everybody's equal, and each of the points here represents the flow, and everybody has the same latency. Okay? So that's what happens when everybody behaves selfishly, and all road links which are used, which have a non-zero flux on a horizontal line. Here, for example, the fourth road is not used by the users because the flow doesn't require it, and everybody has the same travel times. That defines a Nash equilibrium. So the way that works is basically, initially you have a small amount of people. The more people, the more flow. At some point you saturate the first road. What happens next is then people start to move to the second road. So now you basically accommodate people between the first route here and the second route, and the total amount of flow starts to rise, and you continue rising the amount of flow, and you continue filling that diagram. Now the third road has opened, and so on. That's how these Nash equilibrium progressively fill the freeway, and if people behave completely selfishly, this is what you would see on parallel road networks. The beauty of this is that you can show that a Nash equilibrium has a very specific property, which is either all its links are congested, or there's at most one link in free flow. You can show this, and the nice feature of this is that means you can enumerate these Nash equilibrium. There are 2 n of them, where n is the number of links, And that's good because in proving that you can solve the problem in polynomial time, all you have to do is to enumerate for these two n Nash equilibria. And that's the reduction to P of that problem stems from that property. Now, what does that mean? Say, if I have one of these links, that means that everybody's going to be congested except at most one person. And if I think about the amount of flow I could push in that system, then it would amount to say, well, I can be in that context until this guy moves all the way to this point, until at that point I have to move up one level. Okay? Which is what's encoded by that formula here. And it's saying that the most you can push through that system is these Q hats here, which are basically these points. And then the last guy is really the flow you're trying to push on this minus the sum of all the others. Okay? And when you exceed that amount, then you have to move one level up. So that's what happens to push as much flow onto that situation until you move up. And you can characterize that maximum flow you can push through this selfish behavior analytically, and that's part of the solution we provide. Another thing which is interesting to prove, which helps understanding how you can route people, is that you can always show that you can make things better by moving down, and depending on the properties of the latency function, you can prove that moving down is always a good thing, which means this is a case where you have a Nash equilibrium, but that Nash equilibrium is not optimal. So among Nash equilibria, some are better than others, and there is one which is always better, and you can show that for the one which is always better, you have at least one flow which is uncongested. And that's another thing you can prove nicely. So now, what are we trying to do here? We're trying to sort among all the different selfish strategies of people and try to figure out the best one, which means basically computing the argmin of the cost function. It's like among all the possible travel time allocations, if everybody behaves selfishly, and there's many ways to behave selfishly, you're trying to find the best one, and that's called the best Nash equilibrium. And you can show that the computation of that best Nash equilibrium can be done in polynomial time using the enumeration procedure that I've shown before. So now, what about people? What about routing people differently? And that goes into the Stackelberg part of this work. Is until now, everybody's behaving selfishly, you can't control anybody. So now what if we could control 2% of the people, or 3% of the people, by convincing them to leave work later or to use another route? How would you control these 2 or 3% of people in a way that overall society benefits and reaches an optimal? So that's the Stackelberg game I was mentioning before. And in that context, there's R amount of flow, and you incentivize alpha times R to do the right thing for society, and you look at what happens when the other parts behave selfishly. So that's called the Stackelberg game, because you have a leader set, that's the people you can reroute, and you have a Nash-induced equilibrium, which means everybody else behaves selfishly. So there's a Stackelberg-Nash game. And so there's n links, there's R flow, and there's alpha % of the people you can route in this manner. And then you're trying to find among these Stackelberg equilibria which one is the best one, and that's the argmin formula I'm showing. So it turns out that there is something fairly intuitive that does work in that case, which is called the non-compliant first strategy. And the idea is that, if there's 98% of the population you cannot control, you should compute what they would do naturally first, and then fill the rest of the network in a way which is the least damaging possible for society. And so it's a very simple thing. Like you can explain this in an elevator pitch. You probably need 2 floors to explain this, because it's very short. So that non-compliant first strategy happens to be optimal and computable in polynomial time, and that's what I'm going to show next. So what does that mean? That means that you can compute the optimal Nash-Stackelberg solution by enumeration of the 2n Nash games, and showing that among these, with the alpha reroute, there's one which is optimal. So let me illustrate this graphically. If there's 3 flows of selfish people, so forget about the good guys. These are the bad guys. And so here there's k, so let's say 3. What they're going to do is they're going to do the worst thing possible. They're going to try to be selfish. And what that means is they will all have the same latency, because that's the Nash equilibrium we showed before. That means the latency will be on that line, and 2 guys will be congested. This is the fastest route, but it's packed, so you're going slower. This is the second fastest route, but you also go slow because people are congested. And then the third guy has a much longer route, but because it's uncongested, it still takes the same amount of time. So that's the bad guys. And so the idea of the non-compliant strategy is to say, well, the rest of the flows, the people I can actually control, will be filled additionally, but not equally. So for example, I need to put more flow in, so I'm going to put it here. And so far, everybody's still equal. But then when the next guys come in, instead of having everybody suffer, I'm going to just make these guys suffer. So this guy will actually go to the next road, which is much longer. But that doesn't affect the other, who are partly good guys and partly selfish. And what you do is you keep filling the network until you fill all your flow. And when you reach that point, that means you have now filled all your flow. Part of your population is controlled. These are the blue guys. Part of your population is uncontrolled. Okay, so this is controlled. These are the good guys. This is uncontrolled. These are the selfish guys. Not everybody is equal. This guy has a much longer travel time. That's why you should pay him, because you should incentivize him to take the penalty. And these guys, you know, are selfish. You shouldn't pay them. And these guys are really lucky because they're being paid for doing the thing which is the best. So that's probably what you want to be. Basically, you're being paid for doing nothing. You can show that this strategy is optimal. And you can show that, of course, you do it reverse way, right? First, you tell the compliant guy, go this super long route, go this long route, and go this route. And then you let people adjust themselves selfishly, and that gives you this equilibrium. And that's the solution of the Nash-Stackelberg game. That can be computed in polynomial time, and that's mainly due to the form of that latency function. So that's the statement of what I just said with the figures, and I don't think I'll go here now. There's some robustness with this. You can show that you can perturb this in some ways, and as long as the perturbation doesn't exceed bounds, which can be characterized as a function of the capacity of the network, the solution doesn't change. I'm going to skip this. What's interesting, and I'll finish this and then just maybe expand the scope a bit to the end of the talk, is you can compute things which are quite interesting, such as the price of stability, which is the ratio of what would happen if only a portion of people comply versus if everybody complied. Or you could compute what's called the value of altruism, which is what would happen if a portion of the people comply as opposed to nobody complies. Okay? And these ratios characterize, in a sense, how damaging your selfish behavior can be on the network. So going back to that example I showed initially, if you have these 4 routes, this would be 101, that's the fastest. 280 is almost as fast. 880 is much longer because you have to cross one bridge. And 580 is crazy because not only you have to cross one bridge, but you also have to go over the mountain. So that's fairly understandable. So now if you try to route people through that network, and then you progressively increase the flow from San Francisco to San Jose, that's the type of graphs you get. So this is a depiction of the price of stability as a function of demand. So nobody on the freeway, lots of people on the freeway. This must be number of vehicles per lane per hour. And then this is compliance. So nobody complies, everybody's selfish. And then this is a dictatorial state where everybody's doing what they're told. Okay? And so what you can see is pretty intuitive. The price of stability can only increase with decreasing compliance. Okay? It's always bad when people don't do what you tell them. And it's always better if they do what you tell them. And anything in the middle is fair game. And now, in terms of demand, the more demand is not necessarily means that the price of stability increases. It does by jumps, but because it's a ratio, sometimes with networks you have more flow allocated, so the ratio doesn't necessarily increase. The travel time always does, but the ratio doesn't. So this curve is fairly intuitive. And of course, if you're a dictatorial state, that's where you want to be. If you're Berkeley and nobody obeys to the rules, that's where you are. And here is a place where there's no vehicles. So you can kind of map this. And you can plot the reverse, which is the value of the altruism. And you have the same deal. Basically, if you increase demand, the value of altruism goes down. These names are a bit misleading, by the way. We didn't choose them. And then same deal, you can only do worse if your compliance goes down. So the point here was to show that now that we have enough data, these types of policies give us a sense of how you can deal with situations in which a portion of the users can be incentivized. And we're really at a time where just the value of information already provides way for people to change their behavior. TomTom was very successful in creating a 7-hour gridlock by sending everybody to the same spot. So that means if you send people information, they will certainly react to it. And the work we're doing now focuses on the way we should try to do this, either by information sharing or incentivization. So going back to expansion and what we're doing now, I think where we're going with this is, first, massive data fusion. In our system today, we fuse data that comes from satellites, the German DLR. Even at some point, we programmed the satellite to orbit around California so we could gather data. From UAVs, that is, we obtained through the Air Force, and of course all the sources of data that I mentioned before. And the point here is that, one single, we love the phones, but the point is the phones by themselves just won't do it. So data fusion is something which works at global scale only if you integrate all these different sources of data. And the things we do with this, and that's in collaboration with the School of Public Health, is how to use this to predict hour by hour noise levels in cities. Right now, noise levels are predicted at the graduality of 1 year based on traffic counts. But with these models and understanding speeds and all these other quantities we can measure, we can build this into noise models. Other things we're doing with Ron Cohen and Edmund Seno is use this to characterize emissions, and this is the result of a very simple dispersion model that Edmund put together, the Kalman model. It's not going to be 5 years before phones have air quality sensors. It will happen ultimately, and the prototypes are in development. But until that's the case, you can really rely on traffic monitoring to at least infer what emissions would be, and these are things that we're working on. I think the big opportunity for data is data procurement. After the explosion of smartphones, a lot of the federal and state, well, the federal DOT, but certainly the state's DOT, have shown enormous interest in buying data, but they don't know how to buy data. So one of the things that we had to do is to write a procurement procedure for the state of California in which we define the acquisition procedure and the data quality standards. And we are far from understanding how these things work well. I mean, you buy the data by the volume, you buy data by accuracy, how do you define quality, and so on. And so it's just at its infancy, but this is probably going to explode also because the secondary network is just not a small enough place that it can be instrumented. So data from the private sector has to be bought, and there's a lot of challenges with that data. So this is the volume of data that we get from a given provider, and it changes radically from the day to the night. But the point is you don't really care day or night, you care to have data when there's a traffic jam. And the latency, if you give me a GPS point which is 5 minutes old, I can't make any use of it because it's obsolete. So all these metrics are things which are important to take into consideration when doing procurement. The next big thing that is going to happen with this in California is integrated corridor management, ICM. And I think we come from a world where we've been used to instrumenting infrastructure quite well. California has a fairly well-instrumented freeway system with ramp meters, with changeable message signs, with HOV and HOTs, just like in the work which was done here at Georgia Tech on HOT, HOV lanes. And the thing that the Department of Transportation is really interested in investigating with us is, well, if the freeway is already saturated anyway, the only thing you can do, especially in LA, is to start diverting some flow. And if you were even more fanatical, to actually divert people into the transit system, or bikes, like Carrie is doing. For this, you really need to convey that information to people. And so this notion of rerouting a portion of traffic, like I was indicating before, on this very theoretical and preliminary stage, is something we will implement within 2 or 3 years. And there's no way we can ever model people at the individual level, but understanding in the aggregate what should be done so an optimal can be reached is something which is fairly important. And what that means institutionally is that it's really an institutional nightmare. You have to deal with MPOs and state agencies and federal agencies, and you have to make them communicate with transit agencies, and you have to use sensing infrastructure, which is shared between the private and the public sector, have industry partners from which you get data procurement, and potentially run your app yourself, like Carrie's running her own app for her own lab. So that's what we're doing now, and that's fairly challenging. The state of California has given us the mandate to take over 1 freeway in Los Angeles. Everything seems to indicate that 710 is a very good candidate. We hope to be able to start to take over its infrastructure within the next couple of months. And so, if you think about what it takes to take over that infrastructure, that means you're creating an entire decision support system. And the part I've talked about today is is basically the yellow box. The first 15 minutes of the talk, Mobile Millennium, that's the yellow box. That's data coming in and information spitting out. So in a sense, in the last 4 years, we built that yellow box. And in the next 3 years, we have to build the rest. So there's a lot of work. We're recruiting a lot of people, and we're very excited about it. But the point is that doing this is quite challenging. I mean, you have to do forecast, you have to do control, you have to do human in the loop, because there's no way they're going to let a Berkeley run algorithm control the fluid automatically. You've probably all seen the movie The Italian Job, where a hacker takes over the District 7. Well, this is not happening. We have to keep humans in the loop. So the next challenge is, and this is by no means a way to show this is where ITS is going, but these are some of the very exciting avenues which are going to be game-changing in ITS in the next couple of years. And again, this is very biased because these are the things I'm interested in. There's probably another 5 graphs like this you could do. But certainly if you think about what's changing today, distributed and control estimation has traditionally and will play a very significant role in transportation. That's not changing anytime soon. Behavioral economics, like lotteries like they do at Stanford with biology, Prabhakara's group, or eco-driving, this is changing. This is really already disruptive to the field. Social networks is huge, especially with companies like Waze. Procurement and policy is also going to be disrupted with this private sector data. In the next 18 months, you'll have connected vehicles which really start to grow up. I mean, the Android Galaxy S3 has already been sold in 30 million copies in the world, and this is one of the first phones which has full IVI integration with the mirroring protocol, and that's just the beginning. That means your car can now play all your apps if you use that phone. I'm not working for Samsung, I'm not doing commercial. They're not funding our work, by the way. But the point is showing that things are changing, and in 18 months there's going to be a revolution, and that means insurance will be very, very abruptly disrupted. Today, to get an insurance premium, you have to disclose your income level, your credit score, things which are completely irrelevant to your driving. Okay? But tomorrow, and in fact this is happening today with companies like Metromile and so on, you can monitor people and assess the risk based on the data. That's going to be revolutionized. Of course, autonomous driving is what everybody's thinking about, but that's not happening before the next 5 or 10 years. It will completely be game changer, and mobility on demand work from MIT is key there, but this is a longer time horizon. So the pink things are the things I'm interested in, and maybe in the last 2 to 3 minutes, I'll just show a couple things on it. For example, we work with Waze, which is the biggest social network for transport, and we're trying to correlate traffic to postings, and these are the polite postings on traffic, and then we filtered out all the politically incorrect things people post when they disclose their traffic, but you can, and this is where I live, so you can see all what people post when they drive around where I live on Waze, and this provides very interesting information. Other things I'm interested in is, like, I'm advising a couple of startups. One of them is going to provide services in which insurance premiums are actually tailored to your driving. If you're a good driver, there's no reason why you should pay more than a bad driver. And so this Street Owl with Fuel Me app enables to do that, and that's one of the game changers. Another company which is relying on the mirroring protocol is completely diving into the car infrastructure. And again, in 5 years, every phone app will probably be able to be played in most of the major car IVI systems through the mirroring protocol. And so today what we see is a lot of companies interested in building tablets. This is one we built in China, and we're trying to see how it can be commercialized that is completely compatible. So you can either put this in your car or use it as a tablet, and basically all your apps can roll through that system in your car. That's going to be completely game-changing in terms of how data is collected and people interact with their commute. So what are we going to do in the future? We're also working on smart buildings. This is a completely different app where we're trying to monitor efficiency of buildings, and in particular characterizing how people interact with their environment, how much data, how much energy they're consuming. That particular app is basically what we call Energy Eyes. You can scan any device, and with its QR code, it's going to figure out how much energy it's consuming based on sensors we'll also deploy. So here it's like energy disaggregation using these sensing. So the algorithms are very similar to what I showed before, except it's working for buildings, and that's something we're implementing in Singapore. One of the Berkeley has an entire floor that we're instrumented and we're working on. Another thing we did in the past, which was another smartphone thing, is trying to use smartphones to create shape maps. And here the idea is that an accelerometer might have enough accuracy to, if positioned properly, monitor an earthquake. And so we did a lot of early testing of how to use these vast amounts of smartphones to monitor earthquakes. These are shake tables we have at Berkeley. And basically they reproduce earthquakes that have been recorded in the past. So it's not like in Star Trek where you move the camera to look like you're in outer space. This thing is actually shaking for real. And what we were trying to figure out is, how good the signal is and how that can be used. Maybe the last thing I can talk about, so you've seen driving phones, you've seen shaking phones, you've seen energy phones. I want to show you what a swimming phone is. So I brought a little toy here. You can pass it in my last slide. This is one of our 100 floating robots. They're powered by phone as well. And here what we do is, just like for traffic, when we launched Mobile Millennium, we were among the first people to see how to integrate mobile measurements in flow models for traffic. Well, we're doing this also with water. This is what these things look like when they're in the water. This was in the Berkeley swimming pool. So all of these can measure local currents, and they gather the positions on GPS using GPS, and then they can even dive and measure things below the water. The Air Force even wants to throw them from helicopters, so we've tested bringing them from bridges, and people really didn't like it because it was dangerous on the boat traffic. But here the point is, you can collaboratively map things underwater. In fact, we're talking with Google on how to use this for Street View underwater. As you know, Google is interested in doing that. And so we do a bunch of deployment of these in the Sacramento Delta. And the thing which is interesting is that watching traffic and watching water currents is boring, so you have to accelerate all this. It's not fun. But the type of things we do here is, when you navigate in water, you actually have to avoid obstacles. It's quite difficult. So what you will see soon in the video is at some point, these things will start moving as fleets. And what's very difficult here is the motion in unstructured environments, because you're completely uncontrolled. You don't even know the currents accurately. You have at best a shallow water model. And so you can probably see, this guy now starting to move, and you'll see another one moving pretty quickly. And so how to collaboratively reconstruct the currents and map them, you can see now it's adjusting itself, it's adjusting its position to kind of not go into an obstacle. So same algorithm, same philosophy. I think it's been a very exciting time for civil engineering. I think that civil engineering is undergoing a set of revolutions. I think traffic was the first one. I think computing and infrastructure is definitely going to be the next one. Moving sensing has tremendously changed the field. And so I think that in the future, building these infrastructure systems, instrumenting them, and creating the proper policies to operate them is going to be at the key of what we do in water, in traffic, in energy. And I think civil engineers and engineers in general, but civil engineers have a really important role to play in that equation, because we are the ones who build the infrastructure in the first place. So we should be able to operate it better. I want to thank all the PhD students who have worked on this, and also we have a fairly extensive staff of people, in particular software engineers. And the thing which is important is it's actually very hard to build these systems if you don't have professional staff. And so working in that context has been extremely beneficial, and I think provided a very rich environment. So it's been a pleasure to work with all these people. I think I almost exceeded my quota of time, but we're 1 minute over. I don't know how much time things get, but thank you very much again. It was really fun to you. I can take whatever is allowed by the time.
I don't see anyone banging on the door yet, so does anyone want to be helpful?
Sure.